Hello, this is Professor Dan Kernler again. Here we are looking today at section 16.2, where instead of doing double integrals just over a rectangular region, we are doing double integrals over a general region. So we're going to talk in this first video about how to express an iterated integral as a geometric region and vice versa, and try to look at regions and try to perceive whether they are vertically simple or horizontally simple. In the next video, we'll talk about how to find some volumes and how to do some other examples as well. So let's talk about this first example, and let's go ahead and evaluate the region, but then we're more interested in drawing a sketch of the iterated region, which would be the sketch of the region that we are integrating over. So let's see here. First, we are integrating with respect to x. We have an integral from 0 to 1. We're integrating with respect to x, so that will be x squared y from 0 to y. That's all going to be dy. We integrated with respect to x, so that 0 and y are actually x values. Integrating from 0 to 1. So we'll put in the y. We'll have y squared times y minus 0 squared times y dy, which will be the integral from 0 to 1 of then y cubed dy, which is easy enough. 1/4 y cubed, or sorry, 1/4 y to the 4th from 0 to 1, so that will be 1/4. So that's the integral, but let's talk about the region. What region was this integrated over? Y goes from 0 to 1, and x is going from 0 to y. Y goes from 0 to 1, x goes from 0 to y. So you can see, well, x goes from 0 to 1 then also, but it's not the whole region. Let's draw the graph of y equals x. So we're first integrating x. X is going from 0 up to y. If you think of a little rectangle, what we're integrating here, at this end, x is equal to 0, and at this end, x is equal to y. So that rectangle is being integrated from 0 up to y. And then what we're doing is then we're going to add up all of those rectangles from y being 0 up to y equal 1. So the region, oops, that was a terrible line. The region that we are integrating over is the top half of this triangle right here. X is going from 0 over to y, and then we're integrating y from 0 up to 1. So what we want to do now is investigate this a little bit more, try to really wrap our head around what are the regions that we're integrating over. So let's go back to thinking of some Calc 1 stuff here first. If we integrate from a to b of dx, one way to think about that is, well, that's just x evaluated from a to b. That's just b minus a. You can think of that as just the length of the interval. You could, however, also think of integrating a function from a to b. And in this case, that function would be the constant 1. And so you could also think of this as the integral of the constant function 1 from a to b. And so you could also think of this as the area under y equal 1. So like a lot of things that we do, that's kind of the function of one variable, the two-dimensional case. So let's take a look at what would this be if we extend this to 3 dimensions like we're doing here in Calc 3. So here I have the integral from 1 to 3 dy, the integral from 2 to 7 dx. So an easy enough integral to do. This would be the integral from 1 to 3. The integral from 2 to 7 dx would be x evaluated from 2 to 7, and that's all dy. That would be the integral from 1 to 3 of 7 minus 2 dy. That's the integral from 0 to 3 of 5 dy. Oh, not 0 to 3. Where'd my 1 go? 1 to 3. That's 5y from 1 to 3. And that would just be equal to, I'm kind of running out of space here, 5 times 2. So that'd be 10. We can think of this as really just, this is just area. 5 is the length in the x direction. See if I can get a little more space in there. And then 2 is the length in the y direction. And what we end up with then is area. So we just multiply the length in the x direction by the length in the y direction, and we get area. That would be x, y. Let's see, y was integrating from 1 to 3. X is integrating from 2 to 7. And so we end up with that area. However, we could also think of integrating the function 1. Now this function is a function of x and y. This is like a height. So we're integrating a height of a three-dimensional figure where that height is a constant 1. And so instead, we could have considered it a three-dimensional figure. X was going from 2 to 7, and y goes from 1 to 3. We have this region in the xy plane, and then we're just going up 1 unit from that, and we're finding the volume of this three-dimensional, just a rectangle. And so again, these double integrals, they can represent something in 2 dimensions, but then if we have a function with a height of a constant height of 1, then we can also think of them as 3-dimensional. So let's do another extension here, and let's use an integrated integral to solve a familiar Calc 2 problem or Calc 1 problem where you want to find the area between two curves. So we have y equals 1/2 x and y equals x squared plus 1 from x equals 0 to x equals 4. We got to be careful here. We don't want to draw the line first because x squared plus 1 gets pretty big. So by 4, that's almost 20, right? So x squared plus 1 starts out at 1. And then, let's see, at 2, it's 5. And then at 4, it's 17. I missed. Well, it's easy enough to erase. We'll try again. So we'll pretend this is 17 here. This is my y equals x squared plus 1. And y equals 1/2 x actually grows very slowly. Starts off going through the origin. Something like that. Y equals 1/2 x. And we want to find the area between them from 1 to 4. So pre-Calc 3, that would just be an integral from 0 to 4. And we would just take the top function, x squared plus 1, and subtract the lower function, 1/2 x, and just do that integral. So that's easy enough. That'll be x cubed over 3 plus x minus x squared over 4 from 0 to 4. And if we compute that, we should get 64 thirds. So we get 64 thirds, then we get plus 4, but then minus 4. So we get 64 thirds. So that is just Calc 1 there. That's not a big deal. Let's look at Calc 3, an integrated integral. Instead, what we're going to do is we are going to integrate from the bottom curve to the top curve to get a little slice here. So we're going to integrate from the bottom function to the top function, and then we'll add all those up as we go across. The area then, the inner integral, we're going to integrate, I almost said x, we're going to integrate y from negative 1/2 x to x squared plus 1. So we're going to add y up from the bottom curve to the top. And then we are going to integrate all of those with respect to x, and as we add them over, x goes from 0 to 4. And you'll see what's interesting with this is we get integral from 0 to 4. We have y from negative 1/2 x to x squared plus 1. That's all dx still. We're integrated from 0 to 4. We have x squared plus 1 minus, oh, is that supposed to be negative? No, that's not negative 1/2 x. That's just 1/2 x to, let's see, minus 1/2 x. And we are now at exactly the same integral we did above, and so this one will also be 64/3. The point of this is not to say this is how we're going to do the area between curves, but it helps us represent regions and integrating over regions and starting like I'm going to go between the two curves, and so I'm going to integrate y from the bottom curve to the top curve, and then I'm going to add all those up in terms of x from left to right. That skill is going to be crucial as we progress into later topics. Okay, so I think I wanted to do one more example and then we'll call, or no, yeah, I wanted to finish this. Sorry, I got my notes here. I wanted to finish this page here, one more page, and then we'll call it a day for this. We'll call it a video here, not a day, but call it a video. Let's do an integrated integral to try to find the area between these curves. Y equals 3x, y equals square root of x minus 4. So 3x from y equals 0 to 2. So what does it get for y to get to 2? X minus 4 starts over at 4, but I want to figure out what does it get to be y equal 2. Square root of x minus 4. So it would be 8. X has to equal 8. So I want to make sure I go all the way over to 8. That's going to be where that square root function reaches 2. And then y equals 3x grows pretty quickly here. Boy, I mean, at 1, it's already up at 3. So that grows pretty quickly. And we'll just pretend that's a line. All right. We want to find the area between them from y equals 0 to y equals 2. And this one keeps growing. We want to find this area here. Now, if you remember this from Calc 2 or Calc 1, you don't really want to draw that rectangle vertically here. The problem is, if you do that, then you're stuck and you have all these different regions. So that seems like a terrible idea. I think what we want to do instead is draw our little representative piece horizontally. And what we'll do then is we'll integrate to find the area. We're going to integrate x from the left curve to the right. Now we got to be careful. This is y equals 3x. We want to integrate x. So we have to solve for x. X is y over 3. So x goes from y over 3 over to this other one. Now again, this is y equal square root of x minus 4. I need to know what x goes from. So x starts at y over 3, and then we'll need to solve here. Y squared equals x minus 4. X is equal to y squared plus 4. So we're going to integrate from y over 3 up to y squared plus 4. And that'll be from the left side over to the right side. And then once I have those, then I'll add up those little rectangles from the bottom to the top. So once I have those, then I'll add those dy, and y goes from 0 to 2. And again, the point of these area questions is not like you're going to be calculating area. The point is setting up a region like this, we're going to be integrating more complex functions, but we have to know what do we integrate over. Again, the title of this section, 16.2, is we're doing double integrals over general regions, not just rectangular where you go from A to B and then C to D, but now there's some general region in the plane that we have to integrate over. So that's what we're practicing here. Okay, we integrate from 0 to 2. The integral of this is x from y over 3 up to y squared plus 4. We're integrating that dy. Oops, sorry. Integral from 0 to 2, and then that'll be y squared plus 4 minus y over 3 dy. And 1/3 y cubed plus 4y minus y squared over 6, right? Evaluated from 0 to 2. Ooh, 8/3 plus 8 minus the 4/6, so minus 2/3. We have to plug in 0, but they happen to all be 0 here. That won't always be the case. Oh, this is actually kind of convenient because 8/3 minus 2/3 is 6/3, which is 2, plus 8 will be 10. Right, so that will be that particular area. There's an interesting little side note here. I'll let you check about what these three components represent and how they fit in, and we'll check the answer and verify the answer above. But I'm going to leave that to you for an exercise. To kind of what I mean by exercise is just something to maybe pause the video, take 30 seconds, see if you can decide how those three values represent the area of the region up above. So what we've shown here is we did the previous example where we could add up our, kind of make a vertical rectangle and integrate from the top curve to the bottom, and then add them all up from left to right. And what we did in the next example is we made horizontal rectangles. We integrated from the left side to the right side, and then we added all those from the bottom to the top. And these two regions that we've looked at they're both called simple regions, but they had a different orientation. So if here we have y is between one curve and another, so there's some bottom curve, some top curve, and then x goes from A to B. And you have this region here, and this will be, let's see, G1 and G2. All right, y is between those two. We call this a vertically simple region. And if we have x between two functions of y, h1 of y, h2 of y, and then y going from, say, C to D, that particular region we would say is horizontally simple. Just kind of looking ahead here, I think, boy, should we do one more? I think it's not a bad idea. This is a little long video, but I think it would be good for us to finish the next page, and then that'll be a nice segue to pause for the last page. Okay, for the last 3 pages. Let's do the next example here. Find the area of the region bounded by these curves. We're going to do it pre-calc 3, just area, and then we're going to try to do vertically simple and horizontally simple, practicing with that. We have y equal x squared, parabola, x equals 3, and the x-axis. So here is our region. Pre-calc 1, find the area. I mean, we just integrate from 0 to 3 of x squared dx, and that would just be 1/3 x cubed from 0 to 3, and we get 9. So easy enough. So let's practice treating this as a vertically simple and as a horizontally simple region. Vertically simple means we're going to draw a vertical piece, and we're going to add up from the bottom to the top there. Well, we're adding up y, and y goes from 0 up to the parabola. And then we're just integrating dy. And then we want to add all those up. X goes from 0 over to 3. And we're going to add those up, 0 to 3 dx. And we can compute this. This ends up being exactly the same thing. Of course, you can't get a different answer by doing things with a different perspective. The integral of dy is just y. We're evaluating it from 0 to x squared. This becomes the integral from 0 to 3 of x squared minus 0 dx, which is the same integral we did above, and so that's also 9. Should be. No surprise there, right? And horizontally simple, we're going to draw our piece horizontally. We have a little bit of an issue here. We're going to integrate x from the parabola to x equals 3. This bottom part here is the parabola. But we're going to integrate x. So we have to know where x starts there on that left-hand side. Well, this is y equals x squared. If we solve for x, x is plus or minus square root of y. And so what we're doing there when we solve for x is we actually get the two different halves of that. So we have the positive half is the one we drew, and then if we kind of maybe sketch it in red here, the other half, that's the negative half. That's y equals negative square root of x. No, x equals negative square root of y. All right, so we want the positive. We want the positive half. So we're going to integrate from square root of y up to 3 dx, and that'll give me that slice. And then I'm going to add up the y's from 0 up to, oh, we haven't really gotten that far yet. From 0 up to, where's that top one? Y goes up to 9, right? 0 to 9 dy. Now that one looks very different. Let's try this one to see if we get the same thing. 0 to 9. Integral of dx is x from square root of y up to 3. That's all still dy. We get the integral from 0 to 9 of 3 minus square root of y dy. Boy, this seems like a really bad idea to do it this way, but we're just practicing with the different perspectives. 3y minus, and that's y to the 1/2, so the integral will be y to the 3/2 divided by 3/2, so 2/3. Evaluating that from 0 to 9. How in the world is this going to be equal to 9? We have 3 times 9 is 27 minus 2/3 times, and then 9 to the 3/2 is the square root of 9, which is 3, and then cubed. So that's 27. Let's see here. That will be divided by 3. That's 9. 2 times 9, 18. 27 minus, look at that. Also 9. Very inefficient, but also 9. And again, the point here for this one is not necessarily to do this integral and find an area that way. We just want to have some flexibility with which orientation we're looking at. And sometimes you might get stuck on a test doing a particular orientation, and then it dawns on you, oh, I could go sideways on this one and integrate x first and then integrate y. And so all we're doing here is just talking about flexibility. Speaking of, let's look at this last example and see if we can pick a good orientation, and then we'll find this area. We have 5x plus 3y equals 15 is the line. X-axis in the first quad, so we only have the first quadrant. And let me just find the intercepts. If x is 0, y is 5. And if y is 0, x is 3. So there's my line. I'm only in the first quadrant here, so I'm not going to worry about that. The parabola is a downward facing parabola. It's got the negative x squared. Its y-intercept is 5, so that's convenient. It touches there. Its other y-intercept, let's see if or x-intercept, actually, not its other x-intercept. Its x-intercepts, if I set it equal to 0, I don't like the negative, so let me multiply both sides by -1. We'll get x minus 5 times x plus 1. We have -1 is a y-intercept then, and 5 is a y-intercept. This parabola comes through like that, and then it also touches over here at -1. It looks like we want this region right here. So I know I'm writing fast. I'm looking at the clock. I'm like, oh, this video's getting long. But I want to slow down here. And I would like you to, once you get caught up, pause the video and do a quick determination of whether you should do a vertically simple region and draw your rectangle vertically, or whether you should do horizontally. And you should draw your rectangle horizontally and find the integral in terms of x first and then add them up in terms of y. Why don't you pause the video and decide which orientation makes more sense for you. For me personally, I don't really want to look at that top area and find like the pieces going between the curve and itself, which means I have to get the curve. Like that just seems like a bad idea. Now, that doesn't mean that the vertically simple is trivial, because we actually don't have the same top and bottom curve for the whole region. We're going to have to split this up and do two different integrals, two different double integrals. Our area for that first integral will be, let's see, we're going to integrate y first. Y is going to go from the bottom curve. I guess I need to solve that, don't I? 5x plus 3y equals 15. 3y equals negative 5x plus 15. And y will be negative 5/3 x plus 5. All right, we're going to integrate from that negative 5/3 x plus 5 up to the parabola negative x squared plus 4x plus 5 dx. And then we're going to integrate all of those and add those up. Oh, no, that's dy, right? We added dy up from the bottom of the rectangle to the top. We're integrating dy. And then we're going to add those up from x going from 0 to 3. And we'll integrate those from 0 to 3 dx. And then separately, we have the second one. We'll integrate that one from 0 up to the parabola, negative x squared plus 4x plus 5. And then we'll add those up in terms of x going from 3 to 5. So we're integrating with respect to y first. Y goes from 0 up to the parabola. And then x goes from 3 to 5. So we're integrating dx second. Okay. Oof, boy. I'm like recording this at almost midnight. It's like only quiet time in the house. And this is a long video. It's half hour here. I'm sure you are ready to be done. So we'll try to make it through here. We're integrating dy. So that's just y from the bottom curve to the top. And then we're going to integrate that dx. I'll do the second one in a second here. This is integral from 0 to 3 of negative x squared plus 4x plus 5 minus the bottom one. So that actually ends up being plus 5/3 x minus 5 dx. And then the second double integral, that's the integral from 3 to 5 of y from 0 to negative x squared plus 4x plus 5 dx. So that's going to be the integral from 3 to 5, and then that one will just be negative x squared plus 4x plus 5 dx. This is all just tedious. These are all just polynomials. I can let you do that. I don't want to kill your time with that. I do have the answer here if you want to double check. That's 155/6. Okay, this was probably our longest video we've done. This is kind of a longer section. We do have one more video to come, but that is it for this one. And the next video, we're going to talk more about double integrals and do some more interesting regions, and then start integrating more than just one. Right now, we just really integrated over a region where the function was just one. We're just integrating dx or just integrating dy. But how do we do if we have a more interesting function up there? That's really what we're getting to in the next video. So that is it for this video.